I think once we do one or two more lectures, things will become clearer, okay? I just want you to understand the concept here. You can't probably understand everything all at once, but just try to feel the concept, what we are trying to do, okay? A simpler problem here, or not a simpler, but let me put it this way. Actually, before I go there, let's do this. So you might ask, where is K? Where is the feedback gain K? Well, yes, we are trying to minimize J, okay? That's for sure. But you have to understand that X and U are not independent, right? I say, let's make F large, G small, and all that stuff, but X and U are not independent. You want to minimize J, and this is subject to X dot equals AX plus BU. So U and X are still connected. So all this X, even the X final, X and U, they are all connected. So you want to minimize this, but it's subject to this. So this problem, solving this problem, results in the famous LQR solution, the linear quadratic regulator problem. Okay. You can simplify this problem a little bit. You might say, for instance, that X desired is equal to 0. Okay, just to simplify the problem. And say X desired is always equal to 0. Basically, you want the controls always try to be around 0. Right? You could do this. Simplify by saying X desired at T final is equal to 0. So you're basically always trying to go back to the steady state. Always try to go back to the steady state. Right? That's what it means. If T final is equal to 0, that means X is always going back to 0, and the steady state value for X for the linear system is always equal to 0, right? So then it means it needs to go back to 0. So J will be equal to 1 over 2 X T final S X T final transpose plus 1 over 2 0 T final X T final X plus G U dt. So it will look like this now, and the steady state part is only looks at that. You see? And this is usually what we want. In the stabilization problem that we have been looking, we always try to bring it back to the equilibrium point, right? Except in the integral part. The integral controller was trying to move it to a certain place. That was looking at steady states and so on and so forth. But the inner loop, the way I explained it last week, the inner loop is trying to bring everything back to 0, right? So that's exactly what we wanted. We wanted to bring everything back to 0, so here it is. It's back to 0. So the T final needs, now the desired T final is equal to 0, and therefore this looks like that. Okay. Another question you might ask is, of course, when does T final end? I mean, in flight, an airplane flies from Istanbul to New York, it takes what? 9 hours, right? So what is T final? Is it 9 hours? Or is it just one maneuver? Right? Now, you can set this problem up in a different way, and you can even simplify this problem further. Another way of looking at the problem would be like this. J is equal to 1 over 2 from 0 to time infinity that would be another problem. So what does it look like now? It doesn't care about the steady state anymore. Does not care about the steady state anymore. It only looks at X and U And the final time is not a fixed time, it is actually infinite. So this is an infinite time problem. And what it really says is that don't move x too much, don't move u too much. From when to when? Well, forever. Don't move them too much. And this is kind of consistent with what we were trying to do over here. Isn't that what we were trying to do? We were trying to stabilize the inner loop, making sure that x doesn't move too much. And here we have something new, and it says don't move u too much. Okay? Don't move x too much, don't move u too much. When? Forever. Never ever. Yes?
You got this about what we did, this integral going to infinity. Is it reasonable?
Of course. Time goes to infinity. It's an infinite time problem. Which means never ever make x large, never ever makes u large. Do you mean that this might go to infinity because of that infinity? Is that what you mean? Well, if x and u is 0, they will not. They will stay at a finite number.
It's accumulating.
I'm just telling you, in a case where, let's say after 2 seconds, x becomes 0 and u becomes 0. It's at steady state. So you can go to infinity, it will be a finite number. You understand that? Having infinity over here doesn't mean that this always goes to infinity.
I'm taking the errors in that case.
No, not the errors, the x. Let's say this is x and this is t. Let's say x is like this. And u is like this. So it will be just this. And here it will be 0 and 0. So it will be a finite number. It doesn't mean it will go to infinity. Okay. So these are just different variations of the same problem. Okay. I'm just telling you this is more like what we were trying to do. We didn't talk about steady state in this problem. In the inner loop, there was no steady state error problem. Right? In this thing, the inner loop, there was no steady state problem. The integral had a steady state problem, not the inner loop. Right? The inner loop didn't care about steady states. There was not even, we were not trying to track anything. We were just trying to stabilize this. And stabilizing means if you move away from the steady state, you want to come back, right? This is what we were trying to do here. So, which means you don't want to move x too much, you don't want to use u too much. So that's that. And there is no t final time, we want to do it to infinity. And this is the infinite time problem. Okay? So you minimize this j, or you minimize this j, or you minimize this j. And these are all different problems, of course, but the idea is the same. You want to minimize j in such a way that one of those things go back to 0, or they're close to 0. Okay? And this is here, if you optimize this one, this would be the classic LQR problem. Now, LQR means what? LQR means linear quadratic regulator. Okay? And it is the most commonly used controller in the industry. Okay, let me repeat that. LQR is the most commonly used controller in the industry. Okay? And it's the most popular one because it is not asking for find me the desired eigenvalues. It says optimize this problem. So what you do in LQR is you're setting up a problem like that. You find a feedback gain k, and that feedback gain k will move the eigenvalues to a certain point by itself. Whatever that point is, whatever the location of the new roots are, will basically be the roots that will optimize one of these problems. Okay? So that's what it tries to do. Now let me give you quickly then no, I'm not going to give it to you. Okay. So what I'm going to do next is I am going to try to solve this problem. I'm going to say, let's minimize J based on this. And to make the problem simpler, let's just simply say the desired x is equal to 0. Okay? Just to make the problem not as complicated as this one. Let's say the desired x is equal to 0. Let's try to optimize this one here. Okay? Minimize J based on x dot equals ax plus bu. That's the problem now. How do you minimize a function? Did you ever try to find the minimum point of a function? How did you find the minimum point of a function? What is? Take derivative and equate to 0. Right? And that's exactly what we're going to do. I'm going to take the derivative of this one, set it equal to 0, and try to find u that will make this thing possible.
How do we ensure that is it maximum or the minimum?
Good question. If you take the derivative, set it equal to 0, how do we know that it's not the maximum? Well, we don't.
Second derivative?
Well, then you take the second derivative, but taking the second derivative of this is not easy. Of course you can take the second derivative, yes. But that's not easy. Of course you can. But first we need to take the first derivative, right? And set it equal to 0. Okay? And that's what we're going to do. When you take the first derivative, of course we don't know if it's the maximum or the minimum. But the maximum would be kind of funny. The maximum of the solution is probably infinity. Because x can be as large as possible, u can be as large as possible, and then j will be a very large number. Basically, if you have a problem like this, how can I make x and u as large as possible? Well, it means that x goes to infinity, which means find the k that makes this unstable. So if you find k that makes this unstable, x goes to infinity, j will become infinity. So that's your maximum, right? You don't really have a maximum, it goes to infinity. So most probably, if you take the integral, if you take the derivative, set it equal to 0, find the solution, it's probably the minimum. Is it the global minimum? Well, we don't know, because if you have a function like that, and let's say you have something like this. Now that's a minimum, right? That's a minimum. That's a minimum, isn't it? And all have integrals, derivatives equal to 0. In fact, the maximums have that too, right? The integral. But which is the actual minimum of this function? The actual minimum is here. Okay? This is a minimum, but we call it a local minimum. Local minima. Minima. Okay? Local minima. It's local. This local minima. This one is the global minima, because it is the actual minimum of the function. Okay? So when you take integral, take the derivative equal to 0, okay, take the derivative equal to 0, then you might find this one, or this one, and you really don't know which one you found. And that's the problem with optimization. It's not very easy to find the global minimum in optimization problems. Now, the world of optimization, let me give you a little parenthesis, a little information. The world of optimization is a big world. Okay? We can talk about optimization for semesters and semesters. Okay? Not one semester is probably not enough. Okay? Optimization is a big world, and you probably should take an optimization class at some point. Okay? We are not really, this is not really an optimization class, right? I'm just going to give you enough of information so that we can reach the solution for LQR. Okay? I could just write down what the solution is. I can tell you from this problem, k is equal to blah blah, and I can do that now. But I want to do this. I want to do the proof for the LQR problem once, so that you know where this is coming from. After that, things will be very easy. In MATLAB, it is one command. You say blah 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 blah. Enter. Boom. You have your k values. You choose your f, you choose your g, it will give you the solution. Okay? A lot of people are doing that. But you need to know where this is coming from. Okay? That's why I'm giving a little time to explain you where this is coming from. And I'm going to give you the proof, actually, where this is coming from. Okay? And we're going to do it once in this class, and then you are free to use it everywhere, and the application is actually very easy. That's why this is so popular also in the industry, because it's so easy to use. Okay? But before you use it, you need to understand where things are coming from, so you can actually make better decisions when you use this controller. Is that okay? All right. So what are we going to do? We are going to take the derivative of this, and taking the derivative is of course not easy, because we have a matrix, we have a vector, right? And we have all this stuff here, and it's not easy. But we're going to do it, all right? Okay, one more thing. Why is this called a linear quadratic regulator? Regulator means controller. It regulates things, which means it's a controller. Okay, so that's easy. Linear, because the problem is a linear problem. It's a world of linear systems, right? Why is it quadratic? Well, you're looking at the squares of things, right? I mean, xtfx is very similar to saying f times x square, right? You're taking a lot of squares here. This one, this one, this one. So that's why it is a quadratic problem, because you have all these quadratic numbers. Okay? All right. So let me start the painful proof of LQR. It will take a little bit. Okay, so let's define the optimization problem, and we call this optimization problem of a continuous system with dynamic constraint. Optimization problem of a continuous time system. Continuous time system. System with dynamic constraints. So, first what we are going to do is we are going to look at a generic optimization problem, try to solve it, and then apply it to this problem. Okay? The first thing is to make sure we understand the optimization problem. All right, so this is the problem. If you look at this, it is it's a generic form of this one. It's the same thing. Basically, we have a terminal constraint. Not a terminal constraint. We have this. What happens at the terminal at TF? Okay, and this is this, and phi here is more generic. It is just a function, and that function here that looks like this. Okay. This is what happens at the terminal, which is the endpoint. J is what we call the performance index. It's basically a function that we like to minimize, okay? Or sometimes we call it the cost function. Cost function. It's basically the function that we like to minimize. Okay, we like to minimize J. L is a function of x, u, and t, and here we have it. X, u, and t. And J, and we want to minimize J, and this is subject to x dot equals fx ut. And here it is subject to x dot equals x u. And these are not really functions of t and t in this problem, but nevertheless we are keeping this together as if this was a generic problem. Okay, so f doesn't have to look like this in this problem, but as I said, this is the generic one. We are going to use this later to this problem and find some solutions. Now this is a generic problem statement. A function that is a function of t final and x final, a function that is a function of x, u, and t, and the problem is subject to a function x, u, and t, and that x dot. The reason we call it a dynamic constraint is that it is a dynamic constraint, because this is a dynamic system and this is a constraint. Basically the x and u's are connected through this, and because I have this x dot, it is again a function of time. So it is, if you are new to optimization, this might appear to be a somewhat complex problem. But I want to go through this so that you at least have a feel where this is coming from. Okay. Do you understand this part? Are you totally lost by now? I hope you're not. Understand it? You have some questions at least. If you're lost, tell me where you are lost so I can help you. Do you understand this part? The things I explained in the last hour. You understand this part? Do you understand the connection between this and this? That this is a more generic form of the same thing? Except writing all this stuff with that, I'm just expressing it as a function phi, which is actually simpler. Instead of writing this, I'm just writing this as a function f, just to make it look simpler or more generic. And what we are going to do is we are going to minimize J. Minimize J, which means, actually do this. Let me do it this way. U such that J is minimum. Find U. So U is free variable and X is dependent variable. So we are saying find u such that j is minimum in this problem. Therefore, u is free. That's the one I'm going to find. And x depends on u because of this. You can still think of this as x being the state, u being the control. I mean, it's the same thing, right? We're going to apply it over there. So the control is free. We can manipulate the u as we want. And x is the dependent variable, which means this is the result. Okay. I'm telling you, LQR is the most commonly used controller in the industry. It's been used in airplanes, helicopters, unmanned vehicles, satellites, rockets, missiles, everything. Okay? It works amazingly well. All right, so we would like to find variation of j and set it equal to 0. Basically, take the derivative of j, find the variation in j, set it equal to 0. For simplicity, phi is only a function of xtf. So I removed that tf because we really don't have a tf in our problem over here. So that's gone. And write this. And dt. Now, let's just stop here. That's a really great part of this. Now, we are going to take the derivative of j, set it equal to 0, right? But somehow we want to have this constraint somehow involved in that problem. Somehow we want to add this, we want to connect these two, right? We want to set j equal to 0, but it's a subject to that. So we want to connect these two. The way we connect them in these optimization problems, something very smart, okay? So the way we connect it, now pay attention, this is interesting, plus some lambda t f minus x dot dt, okay? Now this is quite interesting. So now I'm going to say minimize j. So how do I minimize j here? I mean, what is new? Okay, I took out the tf because that's not in our problem. That's okay. So it is only this is a function that's a function of xtf only. Okay, that's done. This is the one we had. L is over there, and L, this is just a function. It is a function and as a function of x, u, and t. And here, this is also very similar. This is a function of x and u. So we are still on our way. So if this was going to be used, L was equal to this, whatever that thing over there is. But here, this is new. And this is quite interesting. Now look at this. This lambda here is called the Lagrange multiplier. Lagrange multiplier. Lagrange multiplier. What is f minus x dot? What is f minus x dot? F minus x dot actually should be equal to 0 because x dot is equal to f, right? Right? Okay, so x dot is equal to f. But the problem doesn't know that. This problem doesn't know this. Right? It doesn't know. Now it will know. The problem will find is trying to find u. Okay? But x is the dependent variable, so it will try to minimize j in such a way that x is small. It will try to find u such that x is small. At the same time, in order to make this one small, this part should be small as well. Okay? So how do I make this really small? The way I make this small is if f is equal to x dot. So that's how I make it small. So basically, f minus x dot is almost like I'm trying to add a 0 into the problem. Because x dot should be equal to f, I'm trying to add a 0. But it's not exactly 0 because the problem doesn't know about f and x dot. So I am including this constraint into my optimization problem by adding a 0 to the actual problem. So I'm adding a 0 to the actual problem. That way I include this constraint in my problem. And this one, this is what we call a Lagrange multiplier, which is just a multiplier to this. Okay? And this is how we include the dynamic constraints in our optimization problem. I somehow have to connect this with this. The way we connect is we take this x dot minus f, add it into the problem, and then minimize this one. And now this part of the problem now is in my optimization problem. It is almost like adding a 0 to the problem with something called a Lagrange multiplier. Now, if you really want to know where these things are coming from, I encourage you to read our book. It's in the references. Bryson and Hall are the writers, right? Or are the authors of this book. It's in the references of this class. It's called Optimal Control and Applications or something like that. You need to look at the references. It's a very famous book in optimization. Okay? And this material is actually coming from that book. Okay? It's in the references of this, or in the syllabus. The Bryson and Hall, it's a very famous book in optimal control and in general optimization actually. Okay? So how do you add dynamic constraint into your problem? That's how you add it. F minus x dot is equal to 0. You add it with a Lagrange multiplier. So the optimization problem will try to keep this as small as possible, and therefore it will try to keep it at 0. Okay, it will try to keep it as small as possible. It will try to keep it at 0. At the same time, try to minimize these parts. Okay, that's how you add these things into the optimization problem. So that's my new problem. Now, minimize j. Now we are ready to minimize j. Okay? Now define So I'm just adding this one plus this one together and call it h. This function here has a special name in this optimization theory. It's called Hamiltonian. Now the problem looks like this. J So it's a minus. Sorry. And we are now looking at the changes in J. Basically, we are looking at variations in J and try to set it equal to 0. So we're going to look at this. Okay, so what this means is that let's say I have a function j equals 0 and the function looks like this. What we're looking here is we're looking at the variation of j, and eventually we're going to set this equal to 0, right? Eventually we are going to set this equal to 0 and try to find u from here, right? We're going to set this equal to 0. What does it mean? You know, if it's a variation of j, which means find a point and look at the variation. Okay, you'll go left and right. Right? Let's say this is j, right? And let's say you go a little delta j to one side and a little delta j maybe to the other side. And then look if the change is small. Well, in this case it's not small, because if you go into this point it will become a larger number. If you come here it will be a smaller number, right? Let me maybe plot this a little bigger. J, and let's say this is some x. If you just choose one number over here, let's say this is j, some j1, let's say, and you took a delta j over here and a small variation delta j over here, you will see that the variation will be large, right? But if you take that j over here, you take a variation to this side and to this side, it will be rather small, and in the limit it will be exactly 0. That's how we say that this must be a minimum, because the variation is small. Here the variations are large. You go from this to that, right? Variations are large. If you're at the minimum, variations are small. So what we are looking here is exactly that. We are trying to find the j where the change in j is equal to 0. That's what it means. The change in j is equal to 0. If that's true, then we found the minimum. Of course, this is also true for a maximum, but we can also only find extremum points doing that. So we are trying to look at small variations. We call this, we look at weak variations. Weak variations. Okay, we look at weak variations. So if the problem would be like this, okay, then you would look at this one. Delta j is moving little. Delta j is moving little. But you are not looking at larger variations like this. You're looking at small variations. So what we are trying to do is we are trying to find the j where delta j becomes equal to 0, which means the variation in j is small. So we are not somewhere here, but we are here in this little valley. So we are looking at small variations. Okay, we are looking at this del j is equal to del phi dx of tf del x tf plus. So the first one was a function. I'm looking at the variation of phi. So what we are doing is we are looking at the chain rule. X is a function by itself, right? So therefore we have del phi del x, and then we have the variation on x of t. So it's like the chain rule, right? This is a function and x is a variable, so it's like a chain rule. Plus t0 tf x del x u del lambda here hu is equal to del h del u, and h lambda is equal to del h del lambda. What else? Yeah, that's that. So h is a function here, it's the Hamiltonian, and the Hamiltonian is a function of, right? The Hamiltonian is actually a function of now x, u, t, and lambda. Actually, we can simply, yeah, okay. Well, let's keep it that way. We can even simplify this further, I guess, and make it like that. Okay. So what did I do? Because it's a function, right? It's the derivative of with respect to x, with respect to u, with respect to lambda. Okay. And then I take the second part, whatever is left over there, derivative with respect to lambda times x dot, and then derivative of lambda times del x dot. So because this is a multiplication here, right? You're taking the derivative of everything that's inside the integral and derivative that's outside over here. Yeah?
I'm wondering, how do we take a derivative of x tf? Tf is a time, right? So x tf must be a constant. So it will basically...
It's not a constant in the optimization problem, because x, this is not a desired x. This is the x at the final time wherever x will go. X might go here, xtf, or it might go here, or it might go here. So it's up to you. Remember, I'm trying to find u, right? So depending on how I choose u, x final will end up somewhere else. So there is a variation in u. Basically, you understand what I'm saying? Xt final, at the end it will be one number, but it will change depending on u. Actually, all x's and tf's will change based on how I choose u. So I'm trying to choose the u that will bring j to a minimum, and that might be different xtf's. Understood? Okay. So I will just claim that this one and this one will go, because if you take the derivative of h lambda, where is h? If you take the derivative of h lambda is equal to f. That will be equal to f, and that should be equal to x dot, and therefore these two will go in the problem. Okay. So it will be like this. So that's that. So now we have del J is equal to, should I rewrite this? No. Next thing is I'm going to look at this one. Okay. So I'm just going to look at this one, but let's give a 5-minute break really. I know it's getting a little bit boring, but we have to go through this because, as I said, you have to go through this once in your life. It's okay if you use LQR later without going through the proof again. But I don't want you to be one of those engineers who never saw where this LQR is coming from, because it's so simple to use in MATLAB, or the application is very simple, right? But you need to know where this is coming from. And I want to do this in this class because I know if I don't do it, you will never go back and look at the proof where this is coming from. You're just going to apply the formula that will give you magically good results, okay? And I don't want you to do that. So let's give a 5-minute break. We are almost there. It's not too long, okay? We are almost